right, so let's talk a little bit about increasing and decreasing functions and max and min. So these are all kind of related to each other. We're mostly going to look at this kind of graphically. So we sort of just want to get used to some of the concepts here. It gets a little bit weird if you mix it with piecewise functions. So those are a little bit trickier, but the main idea is not too bad. So the first thing I want to get out of the way is eventually, like later near the end of this month, like starting with like the 21st, and I think the deadline is currently is the 25th. I might extend it a little bit, but test number 1, you're gonna have to take a test in MyLab, which means you have to write answers into a computer, and there are some things that just the way that it's programmed is it's going to automatically grade it, and there are certain things that it's picky about. This in particular, I don't want to talk about that. So all right, so basically the book is and the MyLab grader is only sort of considering this for open intervals. There are some reasons you may or may not want to think about it that way, but we need to think about it that way just to sort of match what the computer is going to expect from us. So I'm always going to talk about it in terms of open intervals. There are sort of some reasons for that, but it's a little subtle. But it's a lot easier to sort of draw a picture than it is to actually sort of write it formally as a sentence. But let's not. So for this one, let's not think about whether or not it exists anywhere else. Let's just look at this. There's this interval I. Sorry, I want to really emphasize that it's an open interval that we're thinking about. Well, increasing means that just the numbers get bigger as you go to the right. The outputs get bigger. So the kind of just means what it says, really. But so the book definition is roughly the same. Get bigger or increase. And there's kind of a mathematical way to say it, and it's in terms of so here's A, here's B, here's f of B, and there's so the inputs are A and B, and then the outputs are f of A and f of B. So just to say it with numbers and functions and inequalities, it's just saying that f of b is bigger than f of a whenever b is bigger than a for for any a and b in the interval I. So we're saying that this is a property of I. The function is allowed to be increasing for a while, and then, well, once we leave I, so it's allowed to be decreasing. It could be constant. Usually, if we want to figure out if we have a larger domain, we usually want to find the biggest interval and just keep going until it's, you know, as far as we can, and have it still be increasing. And we want to figure out you know, what's the largest interval of where it's increasing. So maybe if it changes its mind and starts doing the opposite, then maybe I can call this interval J. So just to sort of use the same picture for both, I'm going to say, you know, a function you know, so maybe I have C and then D. If you know, if f of D is less than, so it's the other, so it's the opposite inequality. I'll write it down over to the right. But so, I mean, so it just means the outputs are getting smaller as you go. Like, if you think of it as the input, if you think of it as time, then as you move forward in time, the function is getting, you know, the outputs are getting smaller, you're getting less and less. Forgot the n in input. I in, okay. So if we have two inputs C and D, then f of the later one, f of, you go forward in time, you have got less because you're decreasing. So this is increasing and this is decreasing. So right now we just want to get used to that graphically. This is a huge major theme in calculus. So, you know, just one step at a time. There's a lot of algebra, and then there's some computations that are very specific to calculus. But you want to get comfortable with just the idea, what does a picture of that look like? So I'm going to say just a tiny bit about this. I'm not saying that this is right or wrong. I'm just saying that this is how my lab is going to grade it, and you just have to sort of have to go along with it. So let's say this function is constant, it goes up, and then it goes down. Let's say it's constant again. So let's say it's a piecewise function. So this is going to be 1. That can be x equals 3, that can be x equals 4. So let me just warn you that this is, the MyLab doesn't like this. It's sort of a reasonable way to think about it, but it's just not what it wants to see. And there's a couple reasons why you might want to think of it their way. just doesn't like closed intervals, and it's true that f of 4 is smaller than every other f of f of 3 or f of 3.5 and so on. So the inequalities are all satisfied, but it's kind of just implied in the statement of the problem is that they're only interested in open intervals. And one thing that's a little bit concerning is it's not necessarily mathematically wrong, but it's a little bit weird that well, if you include the end point of an interval and make it a closed interval, then this interval by itself, it looks kind of reasonable because it is true that all the outputs are bigger than all of the previous outputs when you're in the first interval. And it's the opposite for the second interval. It just happens to be that they both include the number 3. But it would be one thing that happens is that if you say, well, we're not going to include the endpoints ever, we're just going to ask questions about open intervals instead, then this 3 it doesn't instead of belonging to both, it's just kind of it ends up in neither. So it's kind of nice to split things into two like completely mutually distinct categories that are not allowed to overlap. So it's I don't know, people just like to classify things and keep them separate from each other. So what MyLab does want to see, maybe I'll use, so test number 1 on MyLab and on the homework. On the homework, I specifically ask, I go ahead and I write down that I'm asking for open intervals, just so I ask you for the largest possible open interval on which this function is increasing. So there's no ambiguity whatsoever the way I write it down. So here's what they want: the same thing but with open intervals, and that's it. So so increasing on 1 to 3. So that's what we're looking for here. So one other reason why open intervals are kind of nice is that, well, you can always go a little bit to the right and a little bit to the left, as long as it's a very, if you're close to the boundary, well, you can still take a tiny step to the right and the left. So the reason why open intervals are nice is the difference quotient. Is another way of, we're not going to make this connection too much in this class, but it's very deeply connected in calculus. You'll explore this further, but I want you to know about this. It sort of connects things. It's interesting and something to think about. But this is just sort of it's like some trivia, or it's like a true fact. something that's nice to know. So when h is small, the difference quotient is positive. Within intervals where f is increasing. So the difference quotient is just the slope of, you connect two dots, and even if it's bendy, well, you can always connect 2 points on the graph and just draw a line between the two dots. And that's what the difference quotient does. It's a system that automatically takes an x and then a step to the right of what's called h, which we want to think of h as being a small amount. You take a tiny step to the right and you get an upward slope. So stating it, sort of quantifying it in terms of what is the slope, it's a positive number. If you always get positive numbers when you take a base point x and then you jump a little bit to the right or the left and you're always getting positive slopes, that's another way of saying that the function is increasing. It's a little bit, it's a little bit sophisticated, but it has very, very important payoffs. It's kind of the backbone of calculus. So you don't have to worry about it too much right now, but if you understand it even a little bit, you're a little bit ahead of understanding how people think about these things. So difference quotient is negative for, well, we always want to, it's kind of, in calculus, you think you're in situations where you want to think of h being very small. That's what happens when you change the function by a very small amount. Are we going up or are we going down? And if you're in the second interval, if the function is decreasing, that's the same as you take an x, then an x plus h, you apply f to both of those things, and you get negative slope. So so within intervals where f is decreasing, so if h is too big, then you might accidentally jump into a different interval. So the point is h has to be small enough that you don't leave the interval I and to go into a different interval j, because long term you can reverse behavior. But point is if you're inside of an open interval, then you can always go just a little bit to the right or the left and have the same behavior within the entire open interval. So you eyeball it. Right at this point is where I'm no longer constant when I come from the left, and I'm no longer on this increasing part. It's kind of like I'm constant here and I'm constant here, I'm increasing here, I'm decreasing here, and these 3 points that are like on the boundary between two behaviors, they sort of belong to both worlds. But if we want to keep everything completely, if we want to like separate our laundry, so to speak, we just think of those boundary points as being remarkable and kind of their own thing that we consider separately. And then the open intervals are just sort of a whole family of points that are acting the same way. So it's kind of like separating your laundry. It's a little bit organized, and so that's one part of it. That's mostly what I want to say here. I need to talk about max and min. So these are very much related topics. And this is another thing that'll help you think about it the way that they think about it. And the max and min problem is another motivation for sort of splitting things into completely different cases. So again, this is sort of, we're talking about intervals. Well, sometimes we just write max and min for maximum and minimum. Okay, so I'll draw a picture like this, and let's say this is, it doesn't have to be perfect, but let's say that those outputs are 1 and 3, and those inputs are x equals 1 and 2, so y equals f of x. So again, we have to think about it in terms of intervals. So just by example, I'll just say a few words and look and point at the picture. I'll give there's a definition I can give in words, and it's also in the book. But at x equals 1, so we use like the word at to talk about the input, so when or where does this happen, and then what is the output. So at x equals 2, f has and sometimes I like to talk about the outputs. I like sometimes we think of the outputs as being the value of the function. So the value that's obtained, the function spits out a 3. At, or it's if this is like time, if time is the input, it's like a when. But if it's like a location, and then anyways, like what's the altitude at this point, 1 mile away from the origin. So go 1 mile to the right, what's the altitude? It's 3. So that has a relative maximum value of 3. All right. And then minimum, so it's the highest point. Well, not globally. Globally would mean it never, ever, ever gets any higher, but it's on some interval, like say, for example, this one, I could actually draw one that's even larger and it's still valid, but only up to a certain point, and maybe it never gets any bigger, maybe it does, it doesn't matter, but it is at least nearby, it's bigger than all of its neighbors. So it's nearby, that's the smallest value because all of its neighbors are larger. Eventually, if you go far enough to the left, it's no longer the smallest ever. But at least nearby, it's the smallest thing in a small neighborhood. So here's an interval where you're the top of the hill, and here's an interval where you're the bottom of the valley. So relative means kind of like nearby, not necessarily globally. You don't have to be the highest mountain in the world. You're just at the very top of the mountain. Same thing with this one. So nearby. So nearby, you're the smallest that the function gets. So you're at the bottom of a valley. Could be an anthill, it could be Mount Everest, but if you're at the top of any mountain or molehill, so that's what it looks like in pictures. If I want to write this down in words, well, page 100 has the two definitions that are a little bit cumbersome. So we have this interval I. So there is a maximum, the function f has a maximum at c. If f of c is bigger than f of x for all x not equal to c, and in an open interval I containing x. I want to say some instead of and in some open interval. So if you make the interval too big, maybe it's no longer true, but if you can find a small enough interval where you're at the top of the mountain in your immediate surroundings, you're higher up than everybody else, you're at a maximum. So you take any other x in the interval I, and it's like, nope, not quite at the top yet. I'm just a little bit farther downhill, and here's the very top. I could even go farther. I could be a bit bigger than that, and you would still see the same picture. But on some scale, I zoom in close enough, and I'm the top of a hill. So maybe it gets a lot higher. Maybe there's another relative max way up here, but we've definitely got a relative max right there. So it's almost the same sentence, but what's different is I think red will stand out more. So minimum is, if I color this one red, here's a red interval I, and it's f of, here's a red point C, that's an input, then f of c is less than f of x for all nearby inputs in the open interval around C. So the interval, well, don't get too hung up on the fact that it's an open interval or what exactly is it. Just think of it as this specifying that there's some interval is just saying nearby. So nearby, all of the neighbors have slightly or maybe significantly larger values. So this output is smaller than all of its immediate neighbors, and that's relative minimum. So yeah, maybe the bottom of the ocean is over here, but this is just a little tiny dip, but we're at a relative minimum. Okay, so that's yeah, so that's roughly it. Combining it with piecewise functions is maybe the trickiest. So you can pause that and think about it a little bit more, but I'm going to look at that piecewise function. And I just kind of want to give you, like, this is as bad as it could maybe possibly get, and anything more than this would be not really fair. So let's sort of look at increasing, decreasing, max and min, and sometimes it's neither. Sometimes so the way I like to write these instructions so it's completely clear is I ask you to find the largest. So there's so being completely specific. So find the largest possible open intervals where f is increasing, decreasing, and constant means the output is completely you get the same output every time in that interval. And I'll quite often just say max and min for maximum and minimum. And I'm going to give it to you just as this problem. I'm going to write it out as just a picture. And I'm going to do something a little bit weird here. And I don't know, let's just make this -1, -2, 1, 2, 3, 4. +1, +2, 3, 4, and let's make that 5. All right, so sometimes it just piecewise functions are where it gets a little bit weird, but it's just you just stop at any point that looks conspicuous, and you just ask yourself the questions: am I bigger than all my neighbors? Am I smaller than all of my neighbors? And if neither of those is true, then it's neither. But if one of those is true, then it's that one. So that's just analyze each one that's conspicuous, anything that stands out, and just ask those questions. So let's see here. Well, constant is actually kind of the easiest. Sorry, I got these in the wrong order. -2 to -1. Open interval. So that's the largest possible open interval on which the function is constant. And let's try and draw this to scale a little bit better. This is, anyways, so that's, so 2 different intervals on which the function is constant. So that's it for that one. Increasing on, well, it's constant. Well, here it looks like it's going up. That's it. So it's -1 to 0. Let's keep going. It looks like it's going down. Something really weird happens, and then what happens? Well, it looks like it's going down again. Well, that's no problem with that, but it's going down those other times. So decreasing on 0 to 2. And again on 2 to 4. And looks like that's, yeah, so it looks like, well, what intervals did we have? Well, we had, I don't know, let's do blue for constant. Looks like every single one of them usually it's going to fall into one of these cases, or else it's too hard to even draw. Some functions are really super duper crazy, but these are not too crazy. So here's, yeah, let's, just to emphasize it, I did blue for the constant intervals, green for just that one interval where it's increasing. And sure, let's, and as long as I didn't forget to write any of those down, well, yeah, it's most functions that you can actually draw, they're going to sort of split up like this. So now all we've got left is max and min, and then we can call it a lecture here. All right, so let's look at the ones that are kind of in the middle here. So this one, it's not a max or min, it's kind of nearby, it's constant, and it's kind of on the boundary points. You have to be sort of on the interior to be a relative max or min, because we want that open interval. Here, well, you're not larger than or less than anything, because to the left of you, you're equal. You're not bigger or less than these. You're like, it looks like if it went up again, it would be a minimum, but right now it's nothing. So this is not part of the final answer, but something you should think about. So it's not a max or min, because to the left, it's not bigger or smaller. Well, why? Because it's nearby, it's constant. It's on the left side, it's constant. And the same value as what it actually is at x equals -1. So to the right, sure, there's consistent behavior, but to the left, the function values are not bigger or smaller. So you look to the immediate left, everybody's exactly the same as me, so I'm not unique. I'm not less or greater than everybody nearby. Not that it's not the bottom of the valley, because to the left of me, it's completely flat. But let's sort of, x equals 0. Something very similar happens. Let me just throw it out there right now. You can pause and think about it for a minute, but exactly the same reasoning. But x equals 4, same reasoning. So 0 and 2 are a little bit interesting. So I put a closed dot up here, which means the function, as you're coming from the left, you have this piece. As you come from the right, you have this other piece, but it jumps up right at x equals 0. So piecewise, above 0 is equal to 1, 2, 3. I guess that's 4. Left and right pieces are below. So nearby, the left and right pieces are below. So it's like the maximum value is 4, and it happens at x equals 0. So sometimes they just say the maximum is 4. I like to include the word value just to really emphasize we're talking about outputs, but sometimes the book gives an ordered pair to describe the maximum, so you have all that information in one package. I like to use the word values. Other books sometimes do that as well. If it asks for the maximum, then the ordered pair is a safe thing. But if like the MyLab is asking for just a number, and they just ask for the maximum, then they're asking for the value. Or they might ask for the x value at which the maximum occurs, which is this related question: is what's the input and what's the output? But that's what we're looking for here. And then running out of space, I'm going to erase this part down here in the middle. You can, I think we've already got all that we need from that. So x equals 2. So is that anything at all, or we have to at least analyze it because it looks really, really funky, but we just ask ourselves, am I bigger than all of my immediate neighbors? Am I smaller than all of my immediate neighbors? So here we're at y is equal to 1. Well, we look to the right, we immediately see stuff like this, where the function is bigger. It's bigger, the function is bigger on the right, more positive anyway, but it's also, it's not like the same on both sides. I'm not at the bottom of a valley because on the left-hand side it's the opposite. So I'm not at the top because there's more higher, but I'm not at the bottom because there's stuff down here on the left. So I'm not a max because the stuff to the right of me is even higher. I'm not a min. Because the stuff to the left of me is even lower. So that's another reason for the open intervals. It's like if you have open intervals that say where it's increasing or decreasing, then the answer to this problem will be on the boundaries of those intervals. If it's increasing, then well, I keep getting smaller, I keep getting bigger, so I haven't reached a max or a minimum yet. I get to an endpoint. That's something I want to consider as a max-min problem. And calculus, a lot of calculus is about the relationship between these two. And you're getting a head start on that right now, so you want to graphically understand this. We're just sort of picking up a few pieces. You're learning a lot that's going to serve you really well. when you get to calculus class, you'll already, if you do good on this stuff, you'll sort of, this is to a large extent, it's not the only reason, but to a large extent, this is like why people would invent calculus. It's like nice to know, like, you know, how do I, if I have these resources to play with and I have X and Y and I can make a fence, how much grass can I fit, you know, stuff like that. You know, I want to make my output as big or as small as possible. How do I do it? Well, we need to understand max and min. And these concepts are all related, and so some pretty good stuff. So yeah, that's it.